We're going to look at a couple of questions now with regards to partial variations. We're going to try to understand why a relationship is a partial variation, model a partial variation relationship with a table of values, a graph, or an equation, solve problems involving partial variation relationships, and compare direct and partial variation relationships. Okay, so our first question, again, multiple choice question. A taxi charges an initial $3.50 plus $1 per kilometer. What is the cost of a 10-kilometer ride? Well, the first thing I'm going to do is I'm going to want to find out how much it costs just for the 10 kilometers of the ride. So I know that there is $1 per kilometer, and I multiply that by the number of kilometers that I've ridden, which is 10 kilometers, which gives you 1 times 10, or $10. $10 just for the 10 kilometers driven. However, just for sitting in the cab, we're also going to have to pay $3.50. So we're going to have to add that on to the $10 that we pay for the trip. So we pay $3.50 just to sit in the cab, plus another $10 so that we can ride 10 kilometers. So that works out to $13.50. So my answer is going to be B, $13.50. The reason this is a partial variation is because the dependent variable, which in this case would be the total charge of their trip, is not necessarily a certain amount times larger than the independent variable. In this case, we multiply the independent variable, which is the number of kilometers driven, 10, by $1 per kilometer, but then we add on an extra value, which changes the relationship. Okay, now this question here, Cal measures the depth of water in a basin as it drains at a continuous rate. The basin initially holds 15 centimeters of water, and it lowers by 3 centimeters each minute. What are the initial value and the rate of change here? The initial value would be the depth of the water when we start measuring, at the very moment we start measuring. So that would mean that we're at 0 minutes in. So 0 minutes in, the basin initially holds 15 centimeters. So 0 minutes in, we have 15 centimeters of water. So that is my initial value. It lowers by 3 centimeters each minute. Okay, so the rate of change would be 3 centimeters per minute. So my initial value is 15 centimeters. Oh, and it's going down. It lowers by 3 centimeters each minute, so it's actually going to be minus 3, because we're starting at positive 15 and we're going down to hopefully no water in the basin. So the rate of change is going to be minus 3 centimeters a minute, because it's going down by 3 centimeters every minute. So create a table of values that shows the relationship between the number of minutes and the depth of water over time. So when I have 0 minutes, we said that the depth of the water is going to be 15 centimeters. After 1 minute, the depth of my water is going to go down by 3, right? So I subtract 3, that's going to give me 12. After 2 minutes, it's going to go down by 3 again. That's going to give me a value of 9 centimeters. After 3 minutes, the depth of the water will be down by another 3 centimeters, which brings me to 6. After 4 minutes, my depth of my water is down by another 3 centimeters, which gives me 3 centimeters left in the tub. And by 5 minutes, I'm going to drain the last 3 centimeters out of the tub, and I'm going to be left with no water. So create a graph to show the depth of the water over the first 4 minutes. So I've got a plane here to graph it, and this time it's a time depth graph rather than just an XY graph. Remember, when I had 0 minutes, I started at 15 centimeters of water. So here I am. 1 minute in, I'm down by 3 centimeters, so I'm right here. 2 minutes in, I'm down to 9 centimeters. 3 minutes in, I've only got 6 centimeters left. And 4 minutes in, I'm down to only 3 centimeters left. So I've put my dots on, my points on my graph. Now my next question is, should I connect the dots when I'm showing the change in the depth of water over time? Does the water level stay at 15 centimeters for the whole first minute until it reaches that first minute, and then 3 centimeters just disappears like that? No, it's going to go down steadily. So I can actually, using my ruler, draw a straight line connecting those dots. It is possible in this case to connect the dots because the water level is going to go down steadily over the course of it draining out of the basin here. So I can connect my dots. How many minutes will it take for the basin to drain completely? Well, I already checked that on my table right here. How long does it take me when it drains out completely? That means my depth in my water is going to be 0. So the depth of my water is 0, according to this, after 5 minutes. Now, if I were to extend my graph, I'm just going to do this by hand. If I extend my graph, I'm going to see that graphically, I also have, after 5 minutes, the depth of my water is going to be down to 0, which is right here. So it will take 5 minutes for the basin to drain completely. Okay, so that's a question with regards to partial variations. And in this, we didn't come up with an equation, but we did set up a table, and we did graph it. So a partial variation shows a linear relationship between two variables, but it has an initial value that is not 0. In our basin question, our initial value was actually 15. The rate of change is constant, and it can be positive or negative. In this case, we saw a negative rate of change, right? It went down by 3 centimeters every minute. And lastly, the equation of a partial variation relationship can be written as y equals mx plus b. This is different than the direct variation in that we have this additional term, plus b. M represents the slope, or rate of change, and b represents the initial value, or the y-intercept. So just quickly, I'm going to go back to our initial question, which is right here. Based on that, we know that y equals mx plus b is the equation for an initial, or for a partial variation relationship. I know that my m represents rate of change. So m is the rate of change. B is your initial value. So based on that, we can actually give an equation for this particular example, even though we weren't asked specifically to give the equation. But I know that y is equal to the rate of change, which in this case is -3, times x plus the initial value. This would be an equation representing the relationship between the depth of the water and the time that we see here. So it is possible to write an equation to represent a partial linear relationship, partial variation linear relationship.